Good morning, everyone. Okay, let me start with the final plenary speak. So I'm very honored to introduce the Sandra Hirche. Let me introduce. Sandra holds the TUM Liesel Beckman Distinguished Professorship and heads the chair of Information-Oriented Control in the Faculty of Electrical and Computer Engineering at the Technical University of München, Germany. She received the diploma engineer degree in aerospace engineering in 2022, and from the Technical University Berlin, Germany, and the Doctor of Engineering degree in Electrical and Computer Engineering in 25 from the Technical University of München, Germany. From 25 to 27, she has been a postdoc fellow of Japanese Society for the Promotion of Science and at Fujita Laboratory at Tokyo Institute of Technology, Japan, of course. So prior to her present appointment, she has been an associate professor at TUM. Her main research interest includes the learning, cooperative, and networked control with application in human-robot interaction, multi-robot systems, and general robotics. She has published more than 20 papers in international journals, books, and referred conferences. She has received multiple awards, such as the Lunde Schwartz Award for her PhD thesis, the IFAC World Congress Best Poster Award in 25, and together with students, Best Paper Awards of I2P, World Pacific, and IFAC Conference of Manualing and Control of Marine Craft in 1999, and Outstanding Student Paper Award of the I2P Conference on Decision and Control 2018. In 2013, she has been awarded with ERC starting grant on the control based on human models. And in 2019, with ERC Consolidator grant on safe data-driven control for human-centric systems. Sandra is fellow of the I2P and received I2P Control System Society Distinguished Member Award. She has served as I2P Control System Society Vice President for member activities, as a chair for student activities in the I2P CSS. As a chair of the CSS Award, subcommittee on CDC-based student paper awards. And she has been elected member of board of the governors of I2P CSS. She has been co-chair of the IFAC TC 1.5 network control systems and the co-IPC for the 2020 IFAC World Congress. Okay, that's all. So please come there. Sandra.
Thank you very much, Junichi, for the nice introduction. So it's a great pleasure to be here, and for me it's a particular honor and a personal highlight and very heartfelt moment because, as Junichi mentioned, I've been doing my postdoc time here for 2 years in Japan and Tokyo. So it's really fantastic to be back here and in this position. So before I start with my talk on towards trustworthy data-driven control, let me thank my amazing team back at the Technical University of Munich and all the great collaborators that I had a chance to work with in the past years, and of course also the funding agencies making this research possible. Now, over the years, control systems have been successfully deployed in systems of increasing complexity, and by that, also increasing uncertainty. Nowadays, control systems are required to support or envisioned to support autonomous systems, as you see depicted here, for example, in autonomous driving, agriculture robotics, assistive robotics. So systems that operate over, without human intervention over extended periods of time in unstructured and open-ended environments. So these societally important applications, together with the impressive push and progress in machine learning, has also pushed research in our community towards a new direction that's called data-driven control. And by data-driven control, I mean, in general, the confluence between our model-based view from our controls community with the data-centric view of the machine learning community, and I will interchangeably use the terms of data-driven control and learning control here. Now let me introduce in more depth 2 examples that we are working with and where we feel that data-driven control is a promising research direction or a promising approach. The first one is a project on neurorehabilitation, personalized neurorehabilitation for stroke patients and for the upper limb of them. So here you see an exoskeleton of this project from our collaborators in action. And here the human dynamics significantly influences the dynamics of the overall system. And it's often patient-specific, and it changes over the course of rehabilitation. So a model of the human motor dynamics is not only needed in order to guarantee certain safety properties, but it's also important to use to devise rehabilitation protocols such as assisted as needed. And in this case, first principles are only limitedly available. So obviously, those systems have to be safe, they have to be robustly safe, and they have to be reliably operating over extended periods of time. Also transparency in the sense that the system is explainable, predictable, interpretable is important because there's still human supervision and medical diagnostics needed here. Privacy, of course, is also a concern. Now, a second project, very different, still robotics, is in underwater robotics. And this is a project Sea Clear, where an underwater vehicle is supposed to collect litter from the ocean floor. So obviously this requires high precision motion control in order to grasp objects. And this is challenged now by the really highly nonlinear and hard to obtain dynamics of this. And it's also changing over time with the mass and the drag of the unknown objects that you have to grasp. And of course, currents and so on, other environmental disturbances also make that problem much more difficult. So you have to adapt fast to a priori unseen situations. So data-driven control, again, is promising. And again, of course, you need to guarantee safety, reliability, robustness, and also transparency, later also for the certification and for eventual human takeover in case of serious problems. Now, these properties of safety, reliability, robustness, and transparency, they belong to the critical properties that have been identified for trustworthiness. And by with this term trustworthiness, I follow the definition that has been developed within guidelines for trustworthy AI, for example, by US, by the European Union. And in fact, the European Union has just issued and just passed the most comprehensive, or first comprehensive AI regulation. Now, other requirements of trustworthiness are privacy, fairness, responsibility, so that you have a possibility to have a takeover by humans still and to opt out. So obviously, AI-enabled control, specifically here data-driven control, is also required to follow these trustworthiness principles in order to ensure certifiability. So in this talk, I will focus on safety, reliability, and robustness, and also a little bit on transparency, as they are the most common aspects across multiple safety-critical control applications as we consider them here. So the first design choice we'll make, that you see here, we'll opt for a model-based control architecture, where we first derive a process, a model of the process, and then in a second step, model-based control law. This is in contrast to purely model-free control, where you derive the control law directly from the observation of the system in operation. And there are two reasons for that. So one is that those structured models with model-based control, they provide more interpretability, so they're better explainable. And secondly, also they have been shown that they are more data efficient than purely model-free architectures. So in this talk, this talk consists of 3 parts. So I will talk first about guarantees for data-driven control systems and how to make those guarantees robust to previously unseen situations and noisy data. Then we will look into modeling aspects, and at the end, into implementation aspects for real-world applications. Now, a second design choice that you have to make is regarding the modeling paradigm, how you model the process. And as we talk about robustness, for us, it's also particularly important to think about uncertainties and how to capture uncertainties. So there are multiple choices, ranging from our well-known parametric models to neural networks to non-parametric models. And here we'll focus on the last one, so on non-parametric models, and in particular on Gaussian processes. The main reason for it is that they provide uncertainty quantification based on data directly. And so let's briefly introduce some background on Gaussian processes. So Gaussian processes, or in brief, GPs, they provide a Bayesian machine learning technique, and they're well suited to model nonlinear functions. They are characterized, or the Gaussian process prior is characterized by a prior mean function. So they represent a probability distribution over functions. So it's a prior mean function, here indicated in the blue line, and it's also characterized by a covariance function or kernel. And in black, you see here possible realizations of the prior of functions. Now, the objective is to learn an unknown function using training data. And you see here in red the training data, and as you have more training data, the blue posterior mean more and more fits the unknown black function. So the pointwise prediction now, based on or conditioned on these training data, is again a Gaussian variable characterized by the posterior mean, and most importantly also by this posterior variance. And now this posterior variance I would like to draw your attention to in particular. So this posterior variance basically characterizes the uncertainty due to limited training data and due to noise in the training data. So you see here, it's indicated here by the blue shade around the posterior mean function. And if far away from training data, the uncertainty is high, while closer there, it's smaller. So basically, it encodes the epistemic uncertainty, so limit the training data, plus the aleatoric uncertainty due to noise. Another important or relevant thing is that there are closed-form solutions for this posterior mean and variance. Now we will use this explicit measure of model uncertainty in our approaches for robustness. Apart from that, also Gaussian processes have shown quite a success in real applications, mainly because of their good generalization capabilities and also of their high flexibility. They're also allowed to include prior knowledge, and I will talk about that in part 2 of my talk. And one of the drawbacks is computational complexity, but I will address that in the third part of this talk. So let's talk about control now, and performance guarantees in control. And it turns out that many of them can be expressed in terms of a condition on the derivative of a scalar function. Here, if you think about stabilization via Lyapunov, you have to ensure that the Lyapunov function derivative is negative definite. Likewise, if you would like to ensure safety via forward invariance of some set, then you need Lyapunov-like conditions on some barrier function to be satisfied. Now, these derivative conditions are straightforward to analyze if our closed-loop dynamics, this F, is exactly known. So now let's assume we have an uncertain system, and we assume that we can decompose our closed-loop dynamics into a nominal part and an uncertain part. As a result, also we can write the derivative conditions as a composition of a nominal part and an uncertain part. And as we have safety-critical systems, so we've employed a pessimism in the face of uncertainty paradigm and basically look into the worst case, so the pessimistic Lyapunov function derivative, which is given here by the nominal part plus the absolute value of the uncertain part. Now, if you can ensure that this pessimistic derivative is negative definite, then you can guarantee also robust convergence. So now, if we employ Gaussian processes for modeling this uncertain dynamics, then we can directly relate the uncertainty coming from the training data distribution to the robustness certificate of the Lyapunov function. And to this end, we use what's called a uniform quantification of uncertainty for Gaussian processes. It can be shown that the error between the unknown function f and the posterior mean of the Gaussian process is probabilistically bounded by a product with a scaling factor beta. And here you see the posterior standard deviation, which is exactly the relation, gives you the connection to the training data distribution and quality. So with this error bound, we can also now bound our pessimistic Lyapunov function derivative in a probabilistic sense. And most notably, you see here this uncertainty, which depends here on the training data distribution and quality through this term that you see here, and also the gradient of the Lyapunov function. So both the training data distribution and quality in the context and the control task, so in the context of the control task, play a role here. And depending on the training data distribution, you can have either a negative value of a pessimistic Lyapunov function derivative or a positive value. So using level set arguments, then you can conclude to probabilistic convergence to a compact set. So now let's illustrate the importance of considering this epistemic uncertainty. And to this end, we look into the stabilization of an inverted pendulum using feedback linearizing control. We learn the unknown dynamics of the pendulum using a Gaussian process model. However, we only use the posterior mean function. So if we do the nominal Lyapunov analysis, then it turns out the controlled systems is stable. However, if we apply the controller to the real system, or here into the simulation, it turns out it's unstable. So the reason for that lies in this training data distribution. So we see that the training data here in the state space of the pendulum is not well covering the space, in particular not around equilibrium. And this led to an overconfidence and misprediction of the model. So it's really important to consider this epistemic uncertainty, in particular in the light of sparse data. Now, if we had applied our robust analysis as proposed before, we would have seen that indeed, with this training data distribution, we cannot guarantee robust stability. So look at the pendulum state space here, and you see in red are regions where the pessimistic Lyapunov function derivative is larger 0 with high probability. In blue, it's less than 0. And around the equilibrium, you see a large red region, and it turns out we can even show that it's unstable with high probability. Now, if we change to a much more dense data sets, here indicated by the green crosses, then you see the red region shrinks. So, and in fact, we can guarantee probabilistic convergence to a ball around the equilibrium, so ultimate boundedness. And the size of the ball depends on the training data distribution and quality. So in principle, very high level, you could say the more and better training data you have, the tighter the guarantees you can give. So when we have more specific control structures, then we can even get a more specific result. So here, assuming that we have a control or a closed loop control that is given here by a linear part plus, where the unknown nonlinear part is compensated by the GP posterior mean that we learn, so which is, for example, the result of feedback linearizing control, then we can probabilistically bound the closed loop tracking error. And in this case, now this tracking error is probabilistically bounded with a dynamic bound, and this bound is a solution of a differential equation, which is determined in terms of the convergence by the control task itself, and also by the uncertainty coming from the training data distribution around the reference trajectory. So in this case, we get a highly localized bound that depends on the localized training data density. And we have illustrated that here in a simulation. So you see in areas where there's a lot of training data indicated here by yellow, we have a small error bound, which is indicated by this red dot. As soon as we enter regions of less training data, you see the error bound blows up. So this gives us essentially a measure of importance of data with respect to guaranteed performance. And so you can use that in many aspects. Now, we applied our Gaussian process-based control approach in the control for Lagrangian system, in particular in computed torque control. Now, here you see the application in a simulation of an exoskeleton with 4 degrees of freedom. And we assume that we know the parameters of this exoskeleton and the dynamics of this exoskeleton. And in computed torque control, you basically use a feed-forward model of the dynamics. And then, in addition, there's a PD feedback controller. Now, when we don't use, so we assume that this human model is uncertain, the dynamics is uncertain, the impedance is uncertain or unknown. So you see that as a result, with pure computed torque control, we see a high tracking error between the desired green trajectory and the red actual trajectory. Now, if we increase simply the control gain, then you see unacceptably high noise that comes from measurement noise that is amplified due to the increased gain. Now, if we now apply our Gaussian process-based augmentation, so we learn the human dynamics, the human motor model, then you see that the tracking performance is much more increased, and not only is the tracking performance increased, but also we can guarantee with high probability that the tracking error stays within a bound that is here indicated by in red. So for now, our results applied for basically static training data sets, so assuming that we did some offline learning, but the full power of learning control and data-driven control, of course, comes when you have an online learning capability. And this is briefly illustrated here in an example with an underwater vehicle where the hydrodynamics is simulated. And we first learn the dynamics of the underwater vehicle. And you see as in an offline fashion, and you see there's very good tracking here in this first part. However, once a current hit that is around here, you see that there's a divergence of the actual trajectory from the desired trajectory. Now, if we apply now an online learning scheme for Gaussian processes, then you see that as soon as the disturbance hits, there's still a little dent in the performance, However, within very few samples, the disturbance is learned, and the underwater vehicle is back on track. And you see here in green also indicated, again, the high probability tube for the closed loop error. So we can ensure fast adaptation, and we have also shown that you get, with more and more training data, essentially you get tighter and tighter guarantees. You need to use a little bit of different techniques in terms of common Lyapunov functions, because that results in a switching controller. So now so far, we used now this uncertainty estimate in the, that comes from data in the analysis, but you can also use that, of course, in control. And you could, for example, use that as a function to modify your control law, or to detect or to decide whether you want to have new data in your online learning scheme or not. And I will present very briefly 3 examples where this is exploited. So in an uncertainty adaptive learning and control scheme. So the first example, again, it's a pendulum example here in the visualization. We use the uncertainty to decide when to trigger new data in an online learning scheme. And essentially, we use the, as a criterion, the pessimistic Lyapunov function derivative, and to decide, you see here in green, when new data is used. And basically, by that, we can tighten the guarantees, and we do that in a very efficient way, because we only trigger new data when necessary. In the second example, we use the uncertainty to derive control laws that are more cautious. So basically, instead of going through areas with little data, they basically try to use paths through high data density, so where you have a lot of model confidence. To this end, we use a control Lyapunov function approach, and we add a risk measure to that. And in a risk-averse fashion, it will steer the system through the high data, rather through the high data density. And as a result, you see here the result of an example in a simulation where we just had 2 trajectories in black from an unstable system, and we can actually guarantee with tightened guarantees that you get this behavior that the trajectories are steered rather to the areas where we have training data. Now, in the third example, we use that to adapt the gain in the Euler-Lagrange system, so in a robotics system, and basically we would like to balance between the use of an accurate feed-forward model and the feedback. So in areas in the state space where we have little information, we tune up basically our gains to get a good tracking performance. And in an area where we have a lot of data, we rather rely on the feed-forward model. And it balances nicely then tracking and noise attenuation. So, of course, we've not been the only ones who considered GP-based learning, and in particular also investigated the link between the robust closed-loop certificates and this training data distribution as it comes explicitly from the Gaussian process. It just demonstrates that this kind of concept to combine Gaussian processes with model-based control is a very flexible option and can be used with many model-based control approaches. I should also mention there's a huge body of literature in the context of MPC and Gaussian processes that I do not mention here just for the sake of scope and also for the sake of time, but it should be mentioned here. So I'm at the end of the first part of my talk. So where I presented ideas how to directly relate the quality and distribution of training data to robust performance certificates, and we could show that we can give probabilistic convergence guarantees depending on training data directly, rather than on parameters of, for example, a model or of a parameterized uncertainty. Secondly, we also briefly looked into online learning and uncertainty adaptive learning control. Basically, they enable you to get fast adaptation with online learning and tightening guarantees. And also you can exploit this uncertainty measure to basically decide on sampling and adapting control. But one of the key things here is that Gaussian processes give you the possibility to quantify this epistemic uncertainty due to lack of training data and to exploit that in guarantees and also the control design itself. Okay. So far we have relied on a rather generic GP, and so did also our performance certificates. And it makes a lot of sense to look more closely also into the modeling with Gaussian processes. And this is what we are going to do in the second part of this talk. So to apply GPs as a modeling framework in safety-critical systems, we would like to ensure two main properties. The one is that we would like to have them highly accurate, not only in the areas where we have training data, but also beyond that, so having good generalization capabilities. And secondly, they should also reliably represent the uncertainty estimates based on data. And we will look into two solutions here. One is the inclusion of prior knowledge that will address both. And also I will briefly touch upon the importance of looking into the training routines, so the learning for Gaussian processes. Now, while there are multiple ways to include prior knowledge into a Gaussian, into general machine learning techniques, the Gaussian process offers some particular options here. And this is through its prior. So remember, the Gaussian process prior is characterized by the prior mean function and the covariance function or kernel. The first option is through the prior mean, and this is maybe the most standard option to do that. So we assume we have a physics-based or whatever parameterized model available, and we learn the mismatch between the prediction of this model and the output of the real system as a Gaussian process. So you see this is rather straightforward to implement. It's also called hybrid GP. The second option is to look at this kernel or covariance function here. And the idea here is to constrain basically through the kernel the GP function space and embed the physics into the kernel itself. So you basically learn on a submanifold by that, or you could imagine learning on a submanifold which encodes the physical behavior of interest. And we call this physical consistency. And by behavior, that could be qualitative behavior or structural knowledge, like it's a controlled affine system. You could use periodicity of the solutions that you know about as prior knowledge, or also energy conservation or general physical conservation laws. Now, I will present one approach where we guarantee energy conservation. And note that this energy conservation or this physical behavior is then really deterministically guaranteed for every sample of this Gaussian process. So I will present an approach for physically consistent modeling of Euler-Lagrange systems. And here, just as a reminder, we present the classic standard approach, I would say, with a hybrid GP where we learn the difference between a model and something measured and learn that as a GP. So obviously, this is like a black box kind of learning. So even though we introduce prior knowledge, we cannot expect any physical consistency. Now, the idea is now to change the representation here for learning, such that we learn on the manifold of energy-conserving systems. So here concretely for conservative Euler-Lagrange systems. And to this end, we learn the Lagrangian L, which is the difference between kinetic energy and potential energy, with a single GP. We call that the Lagrangian GP. So as a result, we can, for every sample of function, we can guarantee energy conservation. So every prediction has energy conservation. The induced GPs in terms of the torque, because we learned just the Lagrangian here, so we use also the linearity of the differentiation operator to have, again, a GP for the torque. They are conservative. The model itself is lossless, and that's also an important property for example, for convergence proofs that are very often relying on passivity properties in the context of Euler-Lagrange systems. And we also have extensions to dissipated systems available. Now, when we apply this, so he would like to demonstrate the power of this approach by comparing the regression performance of different learning techniques. So we will compare the vanilla GP, which basically ignores any prior knowledge, with the hybrid GP. So by the hybrid GP, we assume that we have a model, but it's 50% off. So it's an approximate model only. And we compare it, of course, with the proposed Lagrangian GP. Looking now at the regression performance, and we do here the mean prediction error volume over the training data, we see that the Lagrangian GP is partially by a magnitude better in terms of regression performance. So it's much more accurate for given training data, meaning that it's also much more sample efficient. You see here the vanilla GP and the hybrid GP in the beginning. So for very low data sets, you have an advantage for the hybrid GP over the vanilla GP, but the wrong model for larger data sets basically gives you a wrong bias in the training data. And not only is the prediction performance superior for the Lagrangian GP, if you look now into the uncertainty, and the prediction uncertainty, it's also by a magnitude better. So we only look here at the scaling factor beta. Remember, this is the error bound that we have from the Lagrangian process, from the Gaussian process. And if you look at here, so we see that the scaling factor is by a magnitude lower for the Lagrangian GP. So we don't show here the posterior variance. Now with this superior regression performance and also the tighter error bound, you can, when you apply that in control, expect much higher tracking accuracy and also tighter guarantees with less data. So again, much more sample efficient with respect to the also the control objective. So the proposed Lagrangian GP, we are currently not only evaluating in simulations, but also in real systems. So here you see current work with colleagues from our university who developed this lightweight cable-driven exoskeleton. It's mechatronically quite difficult to model because of the cables and the friction in it. And we try currently evaluate our approach to model these systems and to do, of course, control with it, model-based control. Another work you see here is in the line of motion prediction, where we use the knowledge that we move on SE3, so the special Euclidean group, and we use the particular SE3 kernel, for example, for motion prediction, for human motion modeling, but also in a recent work with Professor Fujita from University of Tokyo and his team in a visual pursuit scenario. So now I'm at the end of inclusion of prior knowledge, and I would just briefly highlight the importance to think about GPs and the training aspects of it. So the training, so the hyperparameter training for GPs is used, is basically the standard ways to do log likelihood training, which is very good for variance trade-off of the posterior mean. So that's why it's thought to have this good generalization capabilities. Now, it's fundamentally flawed if you think about representing uncertainties, we see that with sparse data, actually, we have quite a high violation rate for this bound. Now, the idea is to take also Bayesian perspective on the training itself, and instead of using the log likelihood optimal, we use a more conservative hyperparameter set, and by that we get a similar accuracy, but with a more reliable uncertainty estimate. So I will not go further in depth into the technical part here, but it's just important to think about where do your uncertainty estimates come from if you have only data. And this is the typical situation when we are in, when we want to apply these things. So I'm at the end of part 2 of my talk, where we looked into physically consistent Gaussian processes and showed that this has a big advantage of using our model-based knowledge and include that in our data-driven approaches. And I briefly skimmed around the issue how to get from data to a data-driven model and really think about where do your prediction bounds come from and the uncertainty. So you need to look into statistical methods to get from those data to data-driven models. So let me come now to the last part of my thought. So we thought now about control performance, about robustness, and about modeling. And finally, I would like to briefly talk about implementation. And in particular, of course, it's interesting when you have resource-constrained platforms. So to this end, we consider an online learning scenario, so where continuously data comes streaming in, which basically increase the number of data, so your Gaussian process blows up. And we look in particular in on a resource-constrained platform, so we implement now the Gaussian process model with the model-based control law on some computationally constrained platform. So we know from Gaussian processes, if you increase the number of training data, then the computational complexity scales with n squared, so quadratically with the number of training data. So you can imagine quickly you lose real-time capabilities if you consider resource-constrained control loop, closed-loop systems. Now, but let's think about what happens if we naively apply online learning scheme on a resource-constrained platform. And this is the behavior that we see. So now we have, again, feedback linearizing control, and we look here at the tracking error norm over the training data. So as expected, with little training data, or as you increase training data here in this regime, you get better and better performance. This is nothing we are surprised about, because with more training data, you get better accuracy and you would expect better closed loop performance as well. So this relates, again, if you want to improve that, so pushing that down means that we have to increase the sample efficiency, so as we just talked about in part 2 of this talk. Now, in this regime, so you see here's a sweet spot, in this regime, suddenly the error again increases. Where does it come from? Well, if you increase the number of training data, eventually a delay will appear here in the prediction from the Gaussian process model to the model-based control law. So you have a delay in the closed loop system, meaning that with more training data, there's more delay, and this delay negatively affects the control performance in a closed loop. So in fact, we can show we have a tracking error bound even with this delay. I didn't put it here, but also we observed that with farther and farther delay, of course, it becomes also unstable in our concrete implementation here. So the key question is, can we devise a more efficient algorithm here? And this is what I will talk about. So there are many approaches available that look into sparse GPs or online GPs. I will present here an approach from our lab that also inherits the formal guarantees that we had presented before. So the idea is now to build up a tree of smaller models that are localized, basically Gaussian process models, and approximate the exact GP by that. And we call that the locally growing random tree of GPs. So as the data stream in to give you an impression of how that works, eventually the training data hit a threshold, and we split the model into 2 models and replace the old model by division rule that I will discuss later. So as more training data stream in, again, one of the leaf models here eventually hits the threshold, and again, we split up the data and therefore also the model into 2. Now, if you do this division rule in a good way, then we end up with a tree construction, and essentially this tree construction has a complexity of log n, and so does also the learning within this tree. So these green things here are now all localized, or for now are also all model GP models with less training data. Now, the key question when we go to the prediction now, obviously for the prediction it's essential how many of those leaf models do we need for the prediction. And this depends on the division rule. And here we propose a division rule which basically, as you go deeper in the tree, shrinks the regions in the state space that this particular model or node is responsible for. So as you go deeper, the state space here is shrinked into these localized model. And here, if you have, for example, a training data, a prediction want to do here, then you only need this localized model, and you can basically forget about the remainder of the tree, so you only have to compute from that model with less training data. So this gives us prediction complexity now from log square n, and combining that, so we have a significantly reduced complexity of log n for the learning, log square n, which of course is, scales much better with training data than n square. And now comes the cherry on the cake. So we can also provide a prediction error bound for this kind of construction, where the only change is now in this red term. Instead of the posterior standard deviation, we have now here a new term, which basically is a fusion of the active model standard deviations. And so this is, we have computational efficiency, and we also compared that, I will not show that, but we compared several classical benchmark data sets with up to 2 million data, and we could show that we have similar regression accuracy as competitors, but much by a magnitude smaller prediction or computational time needed, and in addition we have these guarantees. So we employed that approach also in real systems. So as I mentioned, we work a lot with robotics, and you see here two applications where we employed this log-GP. One is here on the left-hand side, personal assistive control for physical human-robot interaction, prototypical experiment, and on the right-hand side you see the exoskeleton where we implemented a volitional torque observer for volitional torque of the humans, and we so far validated for 1 degree of freedom. Now we expand that to the full exoskeleton. And in our approaches, in fact, this GP learns online with 200 hertz in real world. Okay, I will briefly talk about some extension to this idea. So we have now this modular structure, and we can exploit that in other situations as well. So assume now we have an agent here, like our underwater vehicle, that not only has computational constraint, but also memory constraint. So it's not capable to have all those localized model on its, on its platform. So if this system has access through a communication to like a remote infrastructure that is more powerful, then the idea is to use only very localized models here and to have the whole computation of the tree in this remote infrastructure. And so we offload basically to this more powerful device. We call that network log-GP, and here we basically do a reachability analysis of what is the next most probable model, and localized model too. And this is then exchanged here through communication. Another, so going beyond those tree structures, you can also employ that in multi-agent systems. So imagine now we have a number of agents. Each agents, they are in the same environment, and they want to learn something in the environment and share the learning. So each system here, each agent has a localized GP model. They use consensus type algorithms to come to a joint prediction and basically share the learning in this environment. So, and this is what we call distributed log-GP. And this is possible because we have this modular structure here. So coming now to the end of my last part, so we exploited such a tree-structured approximation of the exact GP in order to get high algorithmic efficiency and regression accuracy. And the nice thing is that we still can provide guarantees. And also we briefly looked into extensions to other computational structures, which I forgot to say, they also have, we also derived guarantees in the same way, and prediction error guarantees, as we did for the original LogGP. So I'm at the end of my talk. I presented elements that I consider important to make trustworthy data-driven control or data-driven control really applicable and certifiable. In particular, we looked into robust performance guarantees for the closed-loop system, given limited and noisy training data. We also saw that using prior knowledge in terms of physics or other knowledge is very helpful in getting a more reliable model. And finally, we looked into computational efficiency, and we have shown that we can bring that to real systems while maintaining the guarantees that we initially have based our results on and certificates. Now, so we introduced basically a framework that provides end-to-end guarantees, and by end-to-end I mean here really from having data to the modeling part, to the design part and closed-loop guarantees, to the implementation. And in our case here, it was really instrumental that we have this database uncertainty quantification, which is naturally, more or less naturally available from Gaussian processes and in conjunction with model-based control. So these are hopefully the first steps to bring us closer to trustworthiness. In a sense here, we looked at safety, reliability, robustness mainly, a little bit on transparency. However, when we really think about the future and how control should support autonomous systems, then of course essential elements are missing. In particular, we need to think about high-dimensional and information-rich problems as they come, for example, from perception and senses. And of course, deep neural networks have shown quite a lot of impressive success here. However, the uncertainty quantification and how to get robust certificates for closed-loop performance out of that is a very open problem. Secondly, you need to think about when you want to have open-ended, long-term operation of your system, you need to think about what have you already experienced, or you have to establish some kind of memory. So a question of transfer learning and experience-based control becomes important. And of course, for long-term operation, naturally you have to interface with planning and symbolic control methods. And of course, as we all want to have these guarantees, we talk about safety critical systems, this is where I believe our community can really contribute to. And with this, I would like to thank you. I would like to thank the organizers again for the great Congress, for really providing all aspects of WA. So this is the theme of the Congress. So harmony, community, and feedback. Thank you very much. Arigatou gozaimasu.
I'm Maria Prandini. I was supposed to chair the session, and I apologize for not being able to introduce Sandra, but now I'm fortunate that I was able to attend all the presentation, and so my greatest congratulations. It was very nice, very well thought, and inspiring. So we have 5 minutes. So if you are willing to make comments or questions, there are microphones. So yeah, I cannot see who did first. Up there, yeah.
So thank you very much for the interesting talk. I have a technical question. So in the guarantee, so we see beta and delta. So can you give a short comment on what is that related to? Thank you.
So delta, basically, typically see 1 minus delta is basically the confidence level by which you want to have the guarantee. So you can choose delta very small, then the probability of the guarantee becomes high. So, and delta is what you design or what you define as a designer. Now the beta, the scaling factor, directly depends on the delta and some properties of the kernel. So it's basically depending on the prior and its delta. The smaller the delta, the larger the beta, you could say. And I talked about the posterior variance, posterior standard deviations used there. This is directly related to the uncertainty coming, or to the yeah, Gaussian process prediction conditioned on the training data. Yeah.
Bob, yes.
Thank you, Sandra. I have a question which it has to deal with the exploration aspects. So in other words, you didn't speak about that part of the active learning. Do you have a comment on that?
Yeah, thank you. Very good question. I think this is one of the, I would say, one of the other holy grails that we have to address, and I think we can address here. There has been some work on active learning, and you can obviously see that you can exploit this uncertainty, yeah, in particular when it's with respect to the closed loop guarantees, to do some active learning. But so we need to think about what is the importance of a certain data point for the closed loop control performance. That's the first thing to do. And then, of course, you have to understand how to reach it. And I think that goes back in terms of the ideas to the ideas of dual control, where you do parallel exploration, exploitation. And I think there's a lot of open questions there and a very rich field that you can do. So it's not only active learning, but active learning in combination with control, I think, is the interesting part.
I think we have still 2 minutes. I saw there was someone on, yeah, and then we are done.
Thank you for the inspiring talk. I have a question about the age of data. If you have a system that is changing over time, can it be that you have to drop all data to improve performances?
Yeah, also very good question and comment. Obviously, if you continuously collect data, your data set becomes larger and larger. That's one thing. But also, if you have time-varying data, time-varying systems, then obviously some of the data become obsolete. And I'm not aware, I mean, you can forget data and so on, but I'm not aware, or at least I would say it's not really matured, to say how to forget the data in the context of time-varying system and how the guarantees then extend. You know, I mean, we still want to give guarantees. You can basically forget, like over the approaches that you forget over a window, you know, you just take the last window of observations, but that might be not the smartest approach. So I think to do the sophisticated approaches to deal with time-varying system is also one of a very interesting challenge.
Thank you.
Okay, thank you everybody. I think we need to thank Sandra again.